Of the Sustainable Transportation Summit. I'd like to welcome Cataline Fotosh to the stage. Cataline, the stage is yours.
Thank you. Thank you very much for inviting me. I've been watching the other presentations, and it is so heartening to see the optimism and the energy that still exists in many areas related to hydrogen, especially hydrogen in aviation. Um, I hate to be the sort of like the Federal Reserve. I wouldn't want to take the punch bowl just when the party's getting started. But we are a regulator. We're more cautious by nature. So I will be talking to you more about things that concern us, hazards, risks, but also pathway to certification and even solutions to address safety risks. So with that, we have published recently this roadmap in December. You don't have to remember the pathway. You can find it in the presentation, or you can just Google FAA hydrogen roadmap and it'll take you to it. We're also putting together a working group. It's a hydrogen aviation working group under ARAC. We've had a little bit of a hold up with changes in the DOT, and we're waiting for some guidance, but we're still on, received nominations, and I'm still hopeful by the end of the summer we have the membership in place. And that is a group that involves some of you. It comes across industry, academia, other regulatory, other federal agencies, and international agencies. We also have a couple of working groups among regulatory agencies. Most importantly, there's an international working group that involves the FAA, EASA, UK, CAA, Brazil, and Canada that is looking right now at gaps in certification regulations and means of compliance and so forth for hydrogen, both fuel cells and combustion engines. And we're aiming for a preliminary report end of this year and a final report middle of next year. So there will be more to come from your dear regulatory agencies. Um, the first thing, and I really don't want to bore you too much because you've probably heard these before. The first thing that comes to mind as a concern for use of hydrogen in aviation is the difference in its energy density between volumetric and mass. So on a mass basis, it has a higher density than hydrocarbons by about a factor of 3. On a volumetric density, however, it's about a factor of 3 again, lower. The good news is that's still a lot higher than batteries. But the implication, the unavoidable implication is the size of tanks. And these are some pictures taken from our friends at ATI who do a lot of very good work on sizing and assessing different hydrogen fueling options. The green ones are liquid hydrogen. The gray ones are kerosene. So you see that there are a lot of embodiments putting hydrogen tanks in the back of the aircraft. And of course, no airline likes to sacrifice cargo or passenger space to put a big hydrogen tank. Therefore, we will have most likely to look at new designs, either stretched fuselage, new designs, and rather than retrofitting, especially for medium and long range transport, rather than retrofitting existing aircraft. And you can tell just looking at this picture that it brings to mind certain concerns, especially with respect to crash worthiness. Currently, we have something that's called tail strikes. And they're quite survivable. They shouldn't happen, but they do happen from time to time, both on takeoff and landing. It will be somewhat more difficult if you have this big tank, thousands of kilograms of liquid hydrogen sloshing violently while it crashes. So crash worthiness, as you'll see later, is something that concerns us. But the most important part, the most important risk that we're looking at is fire and explosion. And that's because hydrogen, although one of the simplest fuels, both in terms of chemistry and property, is a very peculiar fuel. Has the widest flammability range, especially at the rich end. And the central plot here is the one that is of concern mostly to us. The ignition energies, the minimum ignition energies, are about an order of magnitude lower than hydrocarbons and a much wider range of concentrations. And if some of you remember TWA 800, we never found the ignition source for that. And eventually the FAA mandated control of flammability in fuel tanks, not just ignition sources. With hydrogen, having an order of magnitude lower ignition energy, I'm pretty sure we will assume that once you have a leak, it will ignite and that you will have either a flame or an explosion, a hazard. And once you start combustion, hydrogen burns a lot faster than hydrocarbons. This is a comparison of laminar flame speeds between hydrogen and Jet A, and you can see the difference. These are laminar flame speeds. For turbulent, the difference is maintained. Turbulent flame speeds can be several times larger than laminar. It also has a pretty funny behavior, this three limit behavior of ignition temperatures with pressure. Most fuels describe an increasing temperature with increased pressure. So the higher the pressure, the harder it is to ignite. Hydrogen is a very funny fuel because of its chemistry that at both the low end and the high end, it actually gets easier to ignite as you increase the pressure. Hydrogen also has some of the easiest detonability. So detonation is a particularly nasty phenomenon. It's a shock wave followed by a combustion wave with order of magnitude larger increases in pressure rise and temperature. It happens most often in enclosed spaces, but it can also happen in open spaces as long as you have a strong enough initiation, an explosion, for example. And what you have here is something that's called deflagration to detonation time versus equivalence ratio, how much fuel is in the air. And the bottom data are hydrogen. And again, it has the shortest time to detonation and the widest limits of detonability. The one good news is at the low flammability level, although there's still sort of academic disagreement between different people on what those limits are and how they vary with pressure, they're in the neighborhood of 4% or so. And to be honest, the heat release and the radiative flux at near the low flammability limit is not a big concern. So if you call it 4%, it's probably good enough. Now, something we found relatively recently, and we're still looking at, is something that really surprised me as a combustion person, and that is the impact on the combustion of other materials, in particularly materials we find in the cabin. So these are tests where we bring a Bunsen flame to a particular material. In this case, was I think a woven carbon, and we ignite it and then we remove the Bunsen flame. And usually we expect that flame to die out within a certain time and within a certain length. And these are the sort of our guidelines for time and for length failure. The blue line here is time, and the red line is length on the right side of the axis. So what you see here is that, and what was very surprising to me is that even very low concentrations, way below flammability limits, way below anything that I have previously researched in terms of influence on combustion characteristics, right? So 1 or 2% of hydrogen created a significant qualitative and quantitative change in the combustibility of these materials. So the flame length got a lot harder, and basically at 2%, we failed both limits. Similarly, if one measured the heat release using calorimetry, We also found a significantly enhanced combustion rate, heat release rate for these materials. And to be honest, we don't fully understand it. We can hypothesize it. The in a hydrogen environment, you probably have a flame that sits closer to the surface of the material. But I'm not sure we understand it fully. This is an area where more research is needed. Also, at the very low end, very small leaks will sustain a flame. And this is academic research, mostly coming from Professor Sunderland and Axel Baum. Um, they've looked at pinholes, and they put different diameter pinholes and different flow rates. And what they found is that you can support a flame at something incredibly low, 0.05 milligrams, so 5 micrograms. 0.005, I should say. So it's 5 micrograms per second. This is these bottom data. And also, you can sustain a flame 4 orders of magnitude higher at flow rate. 4 orders of magnitude. See, the hydrocarbon limits are somewhere in between. They've also done fittings, so leaking fittings, and you can barely see it here. Of course, hydrogen flames in the absence of contaminants are barely visible because they emit in the UV. And you can tell that hydrogen sits close to the surface, and again, it's self-sustained at very low flow rates. So the question is, if such a leak occurred, is it a hazard? How do we detect it? How do we control it? What do we do about it? They've been worried about these things with vehicles. So SAE 2579 limits such leaks to 5 micrograms per second. But not necessarily in operation or while the car is sitting in a garage. So I guess it's just when you put it together. We're running now some tests with hydrogen leaks in an enclosure, and it does appear that we are able to detect such leaks using something like catalytic hydrogen detectors. But I think more work needs to be done in terms of how do we control these, perhaps with ventilation or shutting off the fuel, because in the end, there is no substitute for shutting the fuel off for eliminating the risk of a hydrogen leak. So I mentioned earlier there are a number of groups at the FAA and other regulatory agencies. We also have industry participation, and there is actually quite a bit of a consensus among different groups and published data on key hazards for hydrogen in aviation. And even in this ranking, so number one, fire and explosion, and I've mentioned earlier leak detection. How would you know which fuel to shut off if you have to shut it off? How do you know if you have enough time to land safely? How would you do safe venting? Today, we can vent an entire kerosene tank, but a liquid hydrogen tank unless you put cryogenic pumps, would be nearly impossible to vent. In terms of crashworthiness, are the current guidelines and safety factors still appropriate for liquid tanks? A lot of the applicants that we are seeing coming with these technologies tend to make a lot of the stuff themselves, whether it's fuel cells or batteries or even fuel tanks, distribution tanks, filters. There's a lot of that. And for example, for tanks, everybody's trying to get a high gravimetric efficiency, right? So the amount of fuel that you carry divided by the fuel tank, the weight of the entire system. And as a result, they use thin-walled stainless steels, things that are less susceptible to embrittlement. But I'm not sure we know enough about the behavior of such double-jacketed, thin-walled vessels with large liquid hydrogen content in them upon an emergency landing, much less a crash landing scenario. I promised to tell you something about certification. I do have to say that we do not have a consensus yet among even within the FAA or even other regulatory agencies as to what the best path for certification of these systems are. Um, and the reason for that is because there are gaps that we're finding in all the current regulations. Um, However, that doesn't mean that we cannot and we do not proceed with applications. So the FAA will do special conditions, and the applicants will actually propose under which CFR they're thinking of seeking transport certificate. There are some things that are fairly clear. The propeller is, we know how to certify that. The electric motor and perhaps the inverter are generally belong in Part 33, although there is some thinking that it could be Part 25 installation. The the consensus, though, is that these special conditions will have to draw from multiple areas of existing regulations and will need additional means of compliance. And this is a shout out to the good people in the different standards committees. Um, we need more standards in aerospace. To the best of my knowledge, today, as of today, there is only one published standard, the 6858, for hydrogen fuel cells for aviation gaseous. There are a number of AIR reports with varying degree of detail and rigor. And of course, there is a whole literature of standards on the vehicle side, NFPA, NASA, you name it. But when you go and look at them in detail, quite often you find that either they don't contain sufficient guidance or the guidance is not really applicable for aviation, where we plan to use these tanks often. They have to be refueled. They don't go just once like NASA. We can't make them very heavy. So there is still a need to keep up the work and issue this guidance faster. And we're more than happy to continue to help and support. Um, we have something called technology readiness levels, certification technology readiness. So as opposed to the like NASA technology readiness. Um, and we have a simpler scale. I know EASA, I think, has something closer to NASA with 9 stages. Ours really has 3 stages: discovery, application, and normalization. And where we find the different key technologies for hydrogen in aviation uh, lying today and in the near future, we see the non-propulsive fuel cells, like the most mature, so uses for emergency power, galley power, and so forth. Um, Propulsive power fuel cells, the second one in terms of their ability to reach certification maturity. There are a lot of designs, startups, companies trying different aspects. And then hydrogen powered gas turbines somewhat lacking or lagging, if you want, even though conceivably it's actually easier to burn hydrogen in a gas turbine engine than to make the entire fuel cell balance of plant, electric motors, controls, and so forth work, especially altitude and so forth. Um, so for gas turbines, that especially those that are relatively low pressure ratios, so except for the most modern ones, it's actually not such a high hurdle to switch them to hydrogen. Um, but there are other questions there because these would be used for medium to long range transport, and the appetite of different companies to push for such technology depends on pull from the market, which in turn depends on availability of hydrogen. And speaking about availability, I'm happy to see there are different possible solutions, especially sort of mobile or scaling solutions at the lower end, because I do believe that it is at the lower end, advanced air mobility, where we are going to see the nearest term progress. That's where there are companies like Joby and Vertical and you name it that are looking at all sorts of different business models for air taxi, freight, um, transportation to airports, between hubs, and all sorts of other applications, as opposed to the longer range, where, as you know, Airbus has delayed their decision, and some of the bigger players have also kind of scaled down their ambitions in the area. This is the rationale behind this. This is a reflection of both the certification readiness and technology readiness. And it's hard to achieve certification readiness until and unless you have some stability in the technology options, which at the current time it's still evolving. This unreadable Excel excerpt here is showing you the kind of detail that we're going through, going line by line through each of the CFR parts, and identify both on the EASA and the FAA side, and identifying where there are gaps, where there are alternative means of compliance and needs for research. So I'm going to end here to try to allow some time for questions or give you back some time. But I think in line with the general optimism in this conference that hydrogen is an option for aviation fuel. I don't know if it's going to save the planet. I don't know if it's going to be a major solution, but at least at the low end, it delivers something that perhaps other options cannot. It delivers scale and efficiency, right? So gas turbine engines don't scale very well at the low end. Fuel cells do. And hydrogen gives you range with respect to batteries. So I'm optimistic that we will see something ongoing at that end. We must treat it with respect. I hope that the things I've shown you have convinced us. And no, the fact that, yeah, we have hydrogen, we're using it. I mean, I used it as a grad student quite safely. We know a lot about it. But I think I also try to impress upon you that with aviation, we are going to be pushing the envelope, whether it's in materials, distribution systems, just the physics of what type of heat exchangers we're going to use, what kind of refueling options. Can we even allow passengers on board the aircraft while we're refueling? Not to even go to issues of liquefaction at airports and transportation distribution within airports. It is not a trivial fact. And I think for now it's looking like a sort of an incremental from below type of diffusion is likely to happen in aviation. But I could be wrong. What I do know, and I don't think I'm wrong, is that these steps that you've seen so far are really just the baby initial steps and sort of putting the framework, putting a plan on the table, getting the players together, increasing awareness, and so forth. Much work remains, and that includes aerospace standards. So with that, I thank you again for your attention, and I'm happy to answer any questions.
Thanks. It looks like there is one question. Would you like me to read it for you?
No, I'm reading it. It's a pretty. We could spend the rest of the day here. It's a big question. So I think some of it I have tried to cover in the presentation. It is difficult to talk in general about the big impacts of using hydrogen in aviation, considering that there are still many options possible, right? So if we're going to use it with fuel cells, for example, if that's the propulsive system choice, um, there are impacts with respect to thermal management, how we're going to ensure thermal management of these fuel cells because they still reject a lot of heat. There are impacts related to carrying reserve battery power, or and looking at batteries. That's an entire area to itself, right? Whether they can go into thermal runaway, they lose capacity at low temperatures, and so forth. Um, how do we handle the purity of the air and ensure, at least the low temperature PEM fuel cells require a fairly pure supply of both fuel and air, because otherwise you could poison the catalyst. Um, and how do we make relatively small filters like this, something that's not the size of the entire airplane? Um, how do we package the entire propulsion system? Do you put separate tanks in the fuselage or wings, or you put everything in a pod? Um, there are generic issues. There are issues that are, and I'm talking mostly about safety impacts, not operations. I don't know enough about the economics of hydrogen to be able to comment competently. And you've seen in this conference people that think hydrogen will be relatively cheap and available, and if that happens, adoption will be a lot easier. Um, but there are still barriers. So to give you an example, um, providing the kind of energy that an airport like Heathrow or Dubai needs, or JFK, would require something of the order of 23 terawatt hours. That's like 3 nuclear plants. And that is just to liquefy the hydrogen on site. So these are daunting numbers and daunting efforts. But again, it doesn't all have to happen at once. In the beginning, you could be flying back and forth from an airport that has hydrogen. You could do multi-fuel combustion engines that they can run on both kerosene and hydrogen. So there are possibilities. I'm very excited to see what is going to happen next. Is Dr. Fotash familiar with the AIAA G095B effort? I'm not that good with the numbers, so I would sorry, for a PhD in engineering, that sounds strange, right? But all these G095B, I would say no. But if you tell me more, I'd be happy to chat on the side. Like who's in it, what exactly do they do, and I might be familiar, just not resonate with the number. Um, Thomas, so be happy to take this offline. Sorry, you're welcome. So I think we stayed pretty much on time, Scott. Really appreciate it and look forward to the next presenters.
Absolutely. Thank you for presenting. Thank you, everyone, for joining us. We'll see you later in the day.